started. Thanks everyone for coming to our first seminar for this semester. Just like to remind everyone that we are recording this seminar. And I'd like to thank Katrina very much for agreeing to be the first presenter. And I'll hand it over to you. So we'll talk for 35 minutes approximately, and then we'll take some questions. Thanks.
So, morning everyone. My name is Katrina. I'm a student at the School of Agriculture and Resource Economics, and I don't think anyone's not from that school this morning, so I don't have to worry. So today I'm going to discuss how marine spatial planning can be improved by incorporating the costs and the benefits of enforcement. So once again, I'm a PhD student here at, under the Centre for Environmental Economics and Policy. Thank you to my supervisors, Dave, Steve and Marit. And this paper that I'm presenting is actually the first chapter in my thesis, and it's currently in press with conservation biology. So these are the details. Hopefully it should be out very soon. So the issue that we're looking at in this analysis is the use of our marine resources. So some of you have probably seen this image before in papers that I've presented. This is an image of our world in the state of the world's oceans in 1910. So there's lots of fish in the sea and there are very few boats trying to catch them. This second image is a more current view. So the date is 2010. There are very few fish in the sea and there are lots of boats trying to catch them. So the problem that we have here is an over-extraction problem. One solution to this over-extraction problem is to restrict the activities that can occur in marine areas. And we do this by creating restricted use management zones. So these zones include no-take areas. So these are areas where fishing activities, other extractive activities, are either partially or completely prohibited. So typically they're no-go zones. The other type of zoning that we can have is a property rights system. So these in fisheries are usually called territorial user rights for fisheries, or TURFs. So in this presentation I'll refer to them as TURFs. And under these zones, fishermen or other resource users are given property rights for the resource, a marine area, in exchange or with the understanding that that will lead to more sustainable use of the resource. So the next question we have is, which areas should we allocate to different zones, and how much area should we allocate to different management zones? And we solve this problem using spatial optimization models. So these models were developed to inform or to evaluate the optimal allocation of area to different activities or zones. So the way these models work typically is a landscape will be divided up into different cells. So these models were initially used in terrestrial landscapes, but increasingly in marine areas as well. So we'll divide our area up into cells, and then we'll incorporate into the model information which helps it evaluate what is the optimal allocation of each cell to different management zones. So an example we can have is looking at 3 marine species, dolphins, sharks, and something that's exotic. We might know where dolphins are found in the landscape. So everywhere that's shaded blue, we assume that dolphins occur. So it's a 1 if there's a dolphin found in that landscape. If we look at sharks, they have a similar distribution, not really. They're everywhere that's grey. In our top left-hand cell, you can see there's a 2, so we assume that both sharks and dolphins are found in this cell. Our little exotic species doesn't get around much and is only found in our top right-hand cell, so limited distribution. So we'd take this landscape model, our knowledge of distribution for these species, and then we'd use our spatial optimization model to come up with an allocation of area to reserves in order to protect each of these species. So I think most of you could guess from this rather simple example that we're probably best off, if we're looking at minimizing the amount of area that has to go into reserve, we can make sure that every species is represented by putting these 2 cells in a reserve. This is all very well and good, but we are economists, and so what we want to think about is costs in the landscape. So we assume that costs are not homogeneous. They may, the example I've shown here is that we assume that it's cheaper to put area into reserves in the south of the landscape, and it's more expensive as you go further north. So area in the north is more expensive, and we don't want to put it in reserves. So if we overlay our cost data with our species abundance data, and then we think about what area we should reserve in order to protect our 3 species, the solution might have changed. In this case, it might be better off if we reserve more area. We start reserving more area in the south rather than less area in the north. So in this analysis, what we were trying to do was to start incorporating some of these economic costs into a spatial optimization model. In particular, we really wanted to determine the impact of including management and opportunity costs on spatially optimal marine zoning. So in this analysis, when we're talking about management costs, we've specifically looked at the costs of deterring poachers and enforcing catch restrictions. So we've looked at enforcement costs. So the case study for this analysis is in Chile. Chile has a very long coastline, 4,200 kilometres. It has very rich marine resources, and it's one of the top 10 countries in the world for marine fisheries landings. So Chile brought in a new fisheries law in 1989 to 1991, and a really big component of this new law was this property rights system, a turf system. So under the territorial user rights for fisheries, fishing groups can apply to the Chilean government for the property rights for specific marine areas. In exchange for these rights, they're responsible for all management. So they have to comply with catch restrictions, and they bear all of the management costs, so including enforcement costs. So in particular in Chile, we've looked at a little study area just 3 hours south of Santiago. So it's a narrow study area. It's about 23 kilometres from top to bottom, and there are 3 fishing groups in the study area. So this is our study area here, this little narrow strip. It's about 800 metres wide. So we're looking at benthic resources and reef fish, so ones that are found close to the shore. So you can see we've divided our landscape up into cells, and there are 96 cells in this case. So what we're looking at then in this analysis is to allocate each of our 96 cells to one of our 5 different management zones. So we've got open access. So in Chile, these open access areas are really heavily exploited. We've got these property rights zones, these turf areas. And here we've made a distinction between turf areas which are enforced. So we assume that there's no poaching, and we assume that catch restrictions are enforced. And areas where poaching, we assume there is poaching, and the catch restrictions aren't enforced. So there's a difference here. So turfs and then enforced turfs. We've made a similar distinction with no-take areas. So in the enforced no-take area, we assume there's no poaching, and we assume that catch restrictions are enforced. So what we're looking at in this analysis is 2 invertebrate species. So these are, on the far left-hand side, that's the Chilean loco. It's very similar to abalone, and it's their major species. And then we have 3 reef fish. So the important thing about these reef fish is that they have very restricted home ranges. So from a study done in 2012, also in conservation biology, by Gelchik et al., we know that there's very high levels of species abundance in these enforced no-take zones, as you might expect. What this analysis also found, again, as you would expect, is that there's very low levels of abundance in these open access areas. So as I mentioned, these areas in Chile there's very heavy fishing pressure. There's not a lot left. What this study found, however, is that these enforced turf zones behave very similarly to enforced no-take areas. So if you have a system of property rights in place and it's enforced, then you get almost as much abundance as you would in a pure no-take area with no catch at all. So this was our data on abundance, and next we were interested in looking into our management costs. So we're looking at enforcement costs. These are necessary to deter poachers, enforce catch restrictions, and in Chile, especially in this area, we know that they vary spatially. So we took data on these enforcement costs from 2 existing turfs. So these are territorial user rights for fisheries turf areas that belong to the El Quisco fishing group. So they've got 2. So we took data on their enforcement costs, what they're spending on enforcing these 2 areas, and we came up with a distribution of enforcement costs based on this data. So areas in our white enforcement bands are very close to fishing groups, and enforcement costs here are very low. So as we get further away from the fishing groups, costs increase, it gets much more expensive to enforce. So the difference is it would cost about US $2,000 to enforce a turf here, and about US $11,000 to enforce a turf here per year. So per year costs. So we took this information, we fitted it onto our landscape, and we calculated the enforcement costs for each of our 96 cells. So here we have data on abundance, and we have data on enforcement costs. And we incorporated this data into our spatial optimization model. So this model allocates each of our 96 cells to one of the 5 different management zones: our open access, turf, enforced turf, no-take, and enforced no-take. And the objective of the model is to maximise fisher revenue from fish caught. So fisher revenue is equal to number of fish which can be caught multiplied by market price. And then if the model allocates a cell to an enforced zone, the cost of that enforcement is also incurred. So we have a very fisher-centric model in that we're looking purely at maximising their revenue. However, we also have a conservation target, and this comes in with our abundance targets. So we set a constraint on the model that we want a given level of abundance present in the study area for each of our species, and we look at different abundance levels. So what we really wanted to get at was the impact of enforcement in all of this, and so we looked at different scenarios. We started off with our basic scenario, scenario A, and in this scenario the model can actually allocate cells to enforced zones. So you see we can only pick up the open access, the turf and the no-take zone. So of course the cost of enforcement isn't incurred either. Our next scenario, scenario B, this is our benefits scenario. So the model can allocate cells to these enforced zones, enforced turf and enforced no-take, but we just get the benefits. We don't actually assume that there's any cost associated with that enforcement. In our second scenario, we say that the benefits of enforcement are there. The model can allocate cells to the open access turf, no-take, and enforced no-take, but we assume that you have to pay for it, so that enforcement comes at a cost. Our final scenario D is the exact same as C, except that we've constrained it to the existing management in the study area, and I'll come back to this. So what we're looking at then is our results from the perspective of fisher revenue, and what we principally wanted to get at was the benefits of enforcement to fisher revenue. So we get this by looking at the difference between revenue under our scenario B, that's our benefits scenario, none of the cost, and revenue under scenario A, so there's no enforcement in that scenario. The difference that we get then is the benefits purely attributed to enforcement. So we looked at a range of abundance targets, 0, 4, 8, and 12%. So this specifies what abundance for our species we want present in the study area. And then you can see on our vertical axis we have US thousands of dollars. So our revenue comes out purely attributed to enforcement is quite high, under 500,000 with no abundance target. And the benefits attributed to enforcement are just under 1.2 million at this higher abundance target. So next we look at costs to compare the two. So we find costs by getting the difference between our benefits scenario, scenario B, and our cost scenario. So both of them have the benefits of enforcement, and then scenario C has the costs. So the difference between them gives us the cost of our enforcement. So these are these yellow bars here. So you can see from the graph that really our enforcement costs are quite negligible compared to the benefits. Our benefits are much larger. There's also benefit cost ratios all greater than 1 and quite a bit greater than 1. So with no abundance target, we have a benefit cost ratio of 5, all the way up to just under 9 with our higher abundance target. So the implications of this is that enforcement of turf areas has net benefits for fisher revenue. Next we go to the graphical element of the analysis, the optimal spatial allocation of the study area. So again, we're just looking at scenario C here, our base case scenario. So enforcement benefits and costs. So we've looked at different abundance targets here, slightly more ambitious than 12%. Most conservation literature would like abundance targets to sit between 20 and 30%. They usually do it by area, we've done it by number of species. So we've looked at 10, 20, 30 and 40%. And this is the allocation of our study area amongst the different management zones. So when we don't have any conservation target, we're managing the study area purely for fisher revenue. The optimal allocation is to put it all into an enforced turf area, into this mustard yellow area. That actually doesn't change as we introduce a moderate abundance target. We still keep everything in this enforced turf. And then as we start to increase that target to 20%, 30% and 40%, some of these no-take areas start to be selected as well. So it's a logical result. The model knows that this is optimal for fisher revenue. It needs to increase its abundance. You get slightly high abundance in these no-take areas, but you don't need it. It's actually cheaper to select this no-take zone without enforcement and stick it in an area that's far away and which would be difficult to enforce. So these are the areas where it's cheap to enforce around our fisher associations. And so the model's allocated those non-enforced zones in these costly areas. implication of this is that, especially for conservation, if we've got conservation objectives in the study area, then we're really looking at a mixture of enforced turfs and no-take in this case as our optimal strategy. So our final question was, how efficient was existing management? So we compared the difference between scenario C. So under scenario C, the model's free to allocate each of our 96 cells to whichever of the 5 management zones that it wants. And then we compared scenario C with scenario D. So in scenario D, same as scenario C, they both have the benefits of enforcement, they both pay for enforcement, but scenario D is constrained by the existing management. So in the study area, there's currently, these are 3 existing turfs which are not enforced. So the Fisher Association, Fisher groups are no longer keeping poachers out, they're not enforcing catch restrictions, and there's 3 well-enforced turfs as well. So what we did, and then there's this wee little no-take in the south. So if a cell overlapped with these existing turfs or no-take areas, we locked it in. So the model for scenario D only gets to play with these white areas in order to meet its objective. Everything else has to stay. So when we look at the difference then between scenario C and scenario D, we're looking at revenue in US thousands of dollars. We can see that across our range of abundance targets, revenue under scenario C is always about US 400,000 more than scenario D. So relative to the magnitude of the revenue that we're actually looking at, this is quite high. So our implication from that is that we know that the existing management in the study area is inefficient. It's a constrained scenario, you'd expect that. So Fisher revenue could be increased if we were free to come up with a new management strategy. So with these results, we wanted to get an idea for the robustness of our results with regards to the enforcement cost. We did a sensitivity analysis of enforcement cost. So here we increased enforcement by a factor of 2, 3, 4, 5, 6, all the way up to 11. And then we've looked at the allocation of the study area as a percentage on the vertical axis. So this yellow line is the amount of the study area allocated to the enforced turf zone. So in our base case, we put everything in enforced turf. As that enforcement cost increases, it's no longer optimal to put everything into the enforced turf, but you have to increase enforcement cost by a factor of 11 before you don't use enforced turf at all. So the other side of this is our open access area. So when we don't allocate area to our enforced turf, we allocate it to our open access. So these 2 lines sum to 100. So when enforcement costs are increased by a factor of 11, you stop managing the study area and you just call it all open access. And that's your most efficient thing to do.
Just a point
Yep.
of clarification.
Yes.
So it could have selected anything, but
Yep.
it always selects open
Yep.
access.
That's it. So that's it. The model wasn't constrained here to just choose between these 2 zones, but this is what it does. Oh, and the reason it does that is because we don't have an abundance target when we looked at this sensitivity analysis. So the model in this case is purely maximizing for Fisher revenue. It doesn't actually need to, it's not constrained by anything apart from maximizing Fisher revenue. The next thing we looked at was the benefit cost ratio under this analysis. So this is on this right-hand side vertical axis. The benefit cost ratio is in this purple curve. So you can see we start at just under 5 in our base case. And then we drop quite quickly. We don't get net benefits from enforcement until we increase those enforcement costs by a factor of 11. So we suspect that enforcement costs could be higher. In the central region, they're probably about right. But in the south of Chile, things are a bit more expensive. There's a lot more poaching. In the north, the situation's different again. So there's room for this enforcement cost to move, but not this much. So we might expect things to be sitting around here, depending on where in Chile you are, but not this high.
So even if you're wrong on the enforcement cost and it would be 3 times higher, it's still worthwhile enforcing.
Yep.
No, then the cost ratio is 1.5.
So this is an interesting result for Chile. So we know that there's net benefits from enforcement. You should be enforcing. It's an optimal strategy for Fisher revenue. But we know that of the roughly 700 turfs in Chile, 300 of them are enforced, and 300 of them are goodness knows what's happening. So we assume that there's poaching going on. So we know that fisher revenue is higher under enforced zones, and we see that fishers aren't enforcing their turfs. So we're investigating this with a survey at the moment. We think it could be a case that fishers are underestimating the benefits of enforcement. Actually, I don't, after doing our survey, I don't think this is it. Fishers are fairly switched on. They know there's a big response between keeping poachers out and having greater abundance. That's a fairly clear relationship for them. It may be that they lack the capacity, financial or time, and this is often the case. So what tends to happen is that they may have people to enforce, and they may have even in early days been able to buy a vehicle to patrol up and down the coast, but there may no longer be excess money for fuel. So they're not able to utilise the capital that they have or buy new capital to enforce. So this is a problem. There could be other biological forces at work. This is, I think, very association group specific. So you assume that all fishing groups have chosen productive areas to have a management area. Otherwise, what's the point? But if for one reason or another they've stopped enforcing and abundance has dropped significantly, it may then no longer be worthwhile for them to enforce. So there's a chicken and egg element going on there. It can also be the transaction costs of enforcement are higher than we've modelled. So fishers are typically enforcing on foot. So the transaction costs involved with monitoring areas which are further away from the collector, they increase quite quickly. There's a different infrastructure that has to be provided for guards as areas get further away. The results that we have at the moment suggest that it's really this last one from the fisher's perspective that they feel that needs to change. So what tends to happen and what should happen is that if a fishing group sees poachers on the horizon or on the shore, everything's done from the shore, they should be able to call the Navy up, and the Navy should respond and deal with the situation. What tends to happen is that the Navy will come the next day or the next week and say, how did things go? And by then it's too late. The other thing that happens is that fishers will catch poachers and they'll take them to the police shop, to the police, again, using their own petrol and their own resources to get them there. And then a few hours later, the poachers are released. Maybe they've told a sad story, or however they've managed to, they might have gotten a slap on the wrist. And then their gear is returned to them and they can be poaching again the same night. So there's not a lot of understanding sort of in the judicial process for what's going on and the value of the resources that are being poached. So there's a lot of sort of social pressures going on here. So again, we're investigating this further. This is chapter 2. So in conclusion, we can say that accounting for enforcement can improve marine management. We know that there are large benefits from enforcement, low costs. These costs do have a spatial component though, and they can be minimised. So if you ask you to guess which of the fishing areas which are still enforced in Chile, they're the ones that are next door to the fishing group. Yeah, so the ones they can see from the tea room of the association, those are the ones that are still enforced. So it doesn't make a lot of sense to have management areas that are far away. We know for conservation that a mixture of enforced turf and no-take zones is probably optimal. And we know that existing management in the study area is inefficient. So largely because we have these expensive to look after turfs in far away areas. Thank you very much.
Questions?
From the biological side, I would find interesting to find out if the people that are involved in the managerial have an idea that there's a continuity of the species within this small parcel that you have measured. But if they don't have this understanding of this movement between them, it's easy to understand why they don't think about preserving the importance of preserving that area. So would you consider including in your next chapter something in terms of how they see the biological factors really having an effect on the abundance and the enforcement management?
So, and you mean, so from the biological perspective, the fact that these species are not fixed, that they move?
Yes.
Yeah. It's an excellent question, Isabel, because that is chapter 3. So what we're looking at is not from the social perspective, but the preliminary results we have suggest that it may, because the bigger species here are the invertebrates, the loco and the keyhole limpet. Loco has a 90 days larval time before it settles. So after being made a larvae, it's 90 days at sea before it settles. What that means is that managing your area sustainably may not have an impact on the number of loco you have next year. So there's a lot of issues in this. That there's very little, if there's very high dispersal of larvae, there's very little incentive for fishers to manage their area sustainably. So on the other hand, it's a slightly different dynamic because loco increases in size every year, and with size it increases exponentially in price. It's not a linear increase. So if you wait a year, you're very likely to get a higher return than you would by banking your money and just getting the interest. You'll make a lot more money if you leave it in the water to the next year. So there are, if you've got the management capacity to manage your resource in the water instead of just out of the water, taking it all out, you can make more money that way. So there's the size of the species increasing, and then there's the fact that your replenishment of stock is very uncertain. Yeah.
Are there any restrictions on fish size and season?
There are. So loco, they went through a period known as loco fever under the military regime, and loco was fished to the ground. It was completely overexploited. And so because of that, they started off introducing just 3-month windows when you could fish, and those 3 months are still in place. But in addition to those 3 months, you have a quota. So each fishing group has a quota. You're not allowed to catch loco if you're not in a management area. So you have to be in that management area to catch that resource. Everything else is on the black market. So, and then they have to be 10 centimetres at least before you can extract them.
I'm just curious, like how can you come up with a number of 96 cells for the first one?
So the size of the minimum size that we had, which we knew was biologically viable to act as an independent sort of nursery growing ground to support a population, was 30 hectares. And so they are all 302,584 metres squared, which is about 30 hectares. So each cell was large enough to be managed independently. And this is important from the biology perspective, because most biologists would encourage reserves to be bigger instead of smaller. And so there's not a lot of science between how big or how connected they should be. So we went for a size that we knew was independent and left it at that.
If you go back to the table which had the 12%, the first set of blue bars, the action, with the 12% restriction.
Yes.
So, we're looking at the revenue that the fishers are getting, and if you impose a zero abundance target, that means the model doesn't worry about the conservation goal, just goes for it and maximises revenue.
So total revenue is not higher. The proportion of revenue attributed to enforcement is that. So total revenue under the zero abundance target is higher than under a 12% abundance target, but the amount of revenue which is directly attributed to enforcement is lower. So as you have a higher abundance target, you need more enforced cells necessarily. So that starts to, your reliance on enforcement increases because you get a higher abundance response, and so the revenue increase attributed to that enforcement increases.
So that's not total revenue that
No.
the fishers are earning.
No.
So my problem was obviously
Yeah.
how are
We should manage it all for conservation. Look, we make more money.
So it's the left, it's just the table, the bar naming, that's confusing, so maybe change
It's
that.
Yeah,
it's
so
the net benefit. It's the difference
revenue attributed to enforcement, and then cost incurred to enforce.
Still need to think
And
about
then
that as to what it means to have revenue that you're going to get from enforcement.
So it's net revenue.
Yeah.
It's the increase in revenue over the base.
That's
So
it.
It's a change in net revenue.
So in this case, the revenue in scenario A is quite low because the model can't allocate cells to any of the enforced zones. And because you get, in all of your cells, you get 0.6% of what's there, because you have to assume that not all your stock is large enough to be caught, and then you have a total allowable catch. But it's still dependent on overall population. So if you have a higher population, you make more money. And because scenario A doesn't have any enforced zones, they have an artificially smaller population, and so they get a lower revenue. So as the model gets more constrained as we go up in abundance targets, and so the ability for the model to increase, actually that's not how I want to describe it.
We have more, because of the higher biodiversity conservation target, we put more areas in restricted catch zones, which means that the populations will get higher, which means that fishers will be able to catch more, which will increase their revenue. And we're not looking at the cost here at all.
Yeah, there's no fishing cost in this. This is all profit or
So
revenue.
If
not
you
profit.
go revenue, I think, well, okay, let's just do one more. Revenue B, enforcement no cost, you've got a particular pattern, and then flip on to the next slide.
And
That's revenue C.
this is
enforcement
flat
cost.
because
Yeah.
everything goes into an enforced zone. So it's
But-
just a flat enforcement cost.
But we're letting them, you're reallocating the areas once you've got the cost on. We're not
Yes.
just doing revenue, not taking B and then saying, okay, well, how much would it cost to actually enforce B? We're actually changing the allocation, the
And
spatial allocation between B and C.
The model is free to do that, but actually it doesn't. So it actually has the same spatial allocation for B and for C. Everything goes into an enforced turf. So, and that's why it comes out as flat, because the model could change the spatial allocation if it wanted to, but it doesn't, because enforcement costs still aren't high enough. This is the base case scenario, so the model's happy to put everything into an enforced zone. And that's why there's no difference here, that they don't change with that target. If it went up to 20%, it would, yeah.
So what's happening to the fish? What time horizon are you looking at?
Which, sorry?
The time horizon?
Yeah,
You are looking at.
we're not looking at
Yeah.
one.
In that time horizon, how do you model what happens to the fish as a result of you having some kind of management system in place?
Absolutely. So at this case, we've assumed equilibrium abundance. So we assume that if you change the management in 2 to 3 years, you will see a different abundance response. So there's no dynamic element in this model. There'll be dynamic elements in the next one. We're looking at a very narrow time window. But in this case, we say that you've had an equilibrium system that you've perturbed, and then after the dust has settled, this is the management, this is the situation that you'll get.
So where do those numbers come from?
So the study that was done, the study that we're basing this data on, they had this data. So they had, they took population counts of areas which had had that management in place for about 7 years, and so we know that basically that abundance was really a function of management, yeah, based on that data. So we know that in Chile, in this system, if you leave everything, if you follow these management patterns, and you leave things for, they suspect 2, probably more like 3 or 5, this is what will happen to abundance. Yep.
I have a minor one. Why is there a cost for a zero abundance target?
The model will still, you make more money if you put things in enforced turf zones, so it'll still put stuff into the enforced turf, and you have to pay for enforcing. So it's not a net cost, it's purely how much are you going to spend on enforcing with a zero abundance target, and you'll spend, I think it's some figure.
Okay.
Katrina, just beyond the zone that you looked at, you mentioned about Chile as a long coastline, and you looked at a case history. If you go beyond that 96 zones, how do you feel about the applicability of what you found here in other areas? You mentioned there are like difference looking at north versus south and so forth. So how do you relate your results back to context?
So
what you have looked at?
what we changed in that case, in the south, it's much more productive. And there's a lot more poaching that goes on. So someone was shot a few months ago over poaching. One of the big issues that I didn't mention actually is that there's a reasonable risk to personal safety for the people who are guarding these areas. So their cars get stoned, etc. And that is much more of an issue in the south. So the benefits are larger you get much bigger loco. Apparently they're not as tasty as the loco in the centre, but they're much bigger, and the price is not sensitive to quality. So you get higher revenue, and because of that you're attracting a lot more poaching. In the north there's a lot of issue with contamination, so you get, again, some places can't even sell their loco because they're right next to a plant which is spewing out toxic waste into the water, and so they can't sell. Up further in the north they have a lower loco, but they're prepared to sell it for lower prices. So there's a lot of interaction that would go on. So certainly you'd have to get that heterogeneity. This model itself could not be applied to all of Chile. You'd have to have more heterogeneity in the abundance if you went north and south, and also the enforcement costs.
So you basically only need to change the parameters.
Yeah, that's it. So the model would work, but the parameters would be different.
Which makes sense.
Yes.
Every time you transfer a model.
So, who are the poachers?
Oh, so according to our recent survey, it's the association themselves, it's other associations, and it's people who are not attached to any association. So
they're all local.
yeah. The problem is that before this turf system came in, the fishery was supposed to be this, as it often is in countries, the fishery is your last resort for people. So if they have no jobs in the city, they come to the coast and they fish during the summer to make up their income. And so there's a lot of social pressure, especially not for outsiders, but for those who are part of the community, to be allowed to poach. These loco will fetch very high prices per individual. So there's a lot of social pressure to allow poaching within the community, but not from others. So if you're from a while away, you can't poach here, but the local youths will often poach and sort of.
Does that explain possibly the non-enforcement, that you're deciding not to have the optimal because
Yeah, absolutely.
they don't want to impose something, so they're going to have to.
Yeah. There's new data coming out on how much is actually being poached, and it's probably quite a lot. So these non-enforced areas could be a lot more productive than we think, but it's not going through. Yeah, there's stuff going on. Social issues.
All right, well, if we don't have any more questions. Thanks very much, Katrina. That was excellent.